What if everything you perceive as reality is merely a holographic projection? A question that at first glance might seem like science fiction, but it's actually a concept that resides within the realm of theoretical physics. It's called the holographic universe theory, and it's as mind-bending as it sounds. This theory proposes that what we perceive as our three-dimensional reality might be nothing more than a projection from a two-dimensional source. Picture a hologram, an image that appears three-dimensional to our eyes, but is actually encoded on a flat, two-dimensional surface. Now expand that idea to encompass the entire universe. That's the heart of the holographic universe theory. Our world, with its depth, breadth, and complexity, might just be a grand holographic projection. But where did this radical idea originate? The roots of this theory are nestled deep within the complex fields of quantum mechanics, black hole physics, and string theory. Quantum mechanics, the science of particles tinier than atoms, has always challenged our perception of reality. It's a world where particles can be in multiple places at once, and where observing a particle can change its state. Then, there's black hole physics. Paradoxically, black holes, the ultimate destroyers of information, led scientists to consider that information about our universe could be stored on a two-dimensional boundary. This idea forms the backbone of the holographic universe theory. And let's not forget string theory, the theoretical framework that seeks to reconcile quantum mechanics and gravity. String theory introduces additional dimensions beyond the three we're familiar with, and in some interpretations, these extra dimensions may host the two-dimensional source of our holographic universe. So, what does this all mean for us and our understanding of reality? Are we living in a grand cosmic illusion, a vast holographic projection, or is this theory just another scientific speculation? And if it's true, what does it say about the nature of existence itself? So, are we living in a grand cosmic illusion? Let's delve deeper into this fascinating concept. The roots of the holographic universe theory spring from the depths of quantum mechanics and the enigmatic nature of black holes. Quantum mechanics, the bizarre and counterintuitive science of the very small, has always been at odds with our understanding of the large-scale universe. This clash is especially evident when we delve into the mysteries of black holes, cosmic entities so dense that not even light can escape their gravitational pull. In the mid-20th century, physicists were grappling with a paradox. According to the laws of quantum mechanics, information cannot be destroyed. However, a black hole seemed to violate this principle, as anything that fell into it seemingly disappeared forever. This conundrum became known as the black hole information paradox. Theoretical physicists Leonard Susskind and Gerard T. Hooft proposed a radical solution in the late 90s. They suggested that all the information about what fell into a black hole was actually encoded in its event horizon, the boundary beyond which nothing can escape. Much like a two-dimensional hologram that can encode three-dimensional information, the two-dimensional event horizon could encode the three-dimensional information of everything inside the black hole. Their idea was a game-changer. It suggested that our three-dimensional universe could, in fact, be a holographic projection of information stored on a two-dimensional surface. This was the seed of the holographic universe theory. Around the same time, another branch of theoretical physics, known as string theory, was gaining traction. String theory proposed that the fundamental building blocks of the universe aren't zero-dimensional points, but one-dimensional strings. It was in the realm of string theory that the holographic principle found fertile ground to grow. The ADS-CFT correspondence, a conjecture in string theory, provided a concrete example of a holographic universe. With these foundations laid, the holographic universe theory began to take shape. The holographic universe isn't just an abstract concept. There are theoretical frameworks and experimental evidence supporting it. To better understand this, let's delve into the ADS-CFT correspondence, a crucial theoretical framework underpinning the holographic principle. ADS-CFT correspondence, short for anti-de Sitter conformal field theory, is a powerful tool conceived by physicist Juan Maldacena. This theoretical framework suggests that a quantum gravity theory in a certain space, like a black hole, corresponds to a quantum field theory defined on the boundary of that space. In simpler terms, it's like a three-dimensional puppet show where the puppets representing our reality are in fact controlled by strings from a two-dimensional boundary. Now, let's pivot to experimental evidence. Here, quantum entanglement plays a significant role. Quantum entanglement is a phenomenon where particles become interconnected, and the state of one instantly influences the state of the other, no matter the distance between them. It's like having two dice, light years apart, that always show the same number when rolled. In 2017, a groundbreaking experiment demonstrated that some quantum entanglement patterns resemble a holographic encoding of two-dimensional information, providing compelling evidence for the holographic universe theory. The results suggested that our perceived three-dimensional reality might indeed be a holographic projection from a two-dimensional source. The interplay between ADS-CFT correspondence and quantum entanglement paints a fascinating picture of our universe, one where every bit of information is interconnected and everything we perceive is a projection from an underlying, simpler reality. It's a picture that shakes the very premises of our understanding of space and time. These factors lend credence to the theory, but it's not without its critics and alternative interpretations. As we navigate the vast expanse of the cosmos, it's crucial to remember that every theory, no matter how brilliant, is an attempt to make sense of the sublime mystery that is our universe. Like any scientific theory, the holographic universe theory has its skeptics. The idea that our three-dimensional reality could be a projection from a two-dimensional source is, let's face it, a bit mind-bending. Some critics argue that the theory is highly speculative, lacking direct empirical evidence. Theoretical physicists are still struggling to develop experiments that can test the theory in a definitive way. Another critique comes from those who argue that the holographic universe theory is simply another form of dualism, a philosophical concept that separates mind from matter, or, in this case, two-dimensional from three-dimensional reality. This separation, they say, is a mistake, a product of our limited human perspective. Then, there's the issue of complexity. The mathematics involved in the holographic universe theory is incredibly advanced, involving concepts from quantum mechanics, black hole physics, and string theory. Some argue that this complexity is a weakness, suggesting that the theory is too convoluted to accurately represent reality. But let's not forget the strengths of the theory as well. The holographic universe theory offers an intriguing solution to the black hole information paradox, which has puzzled physicists for decades. It also provides a theoretical framework for understanding quantum entanglement, a phenomenon that Albert Einstein once referred to as spooky action at a distance. When it comes to alternative theories of reality, there are several. Some physicists argue for a multiverse theory, which suggests that our universe is just one of many. Others propose that we live in a simulated universe, a sort of cosmic computer game. Each of these theories has its own strengths and limitations, and none have been definitively proven. Despite these critiques, the holographic universe theory continues to challenge our understanding of space, time, and reality. It's a theory that pushes the boundaries of our knowledge, inviting us to question our assumptions and explore new possibilities. And that, after all, is what science is all about. Living in a holographic universe. What does that mean for us? In the grand scheme of things, the holographic universe theory paints a picture that is both bewildering and captivating. It challenges our very conception of reality, leading us to question not just what we perceive, but how we perceive it. Let's consider space and time. Traditionally, we see these as separate entities, independent of each other. But within the framework of a holographic universe, they are intertwined, inseparable. They form a single unified field that exists not in three dimensions, but two. This perspective doesn't just alter our understanding of the universe, it revolutionizes it. Now think about existence itself. We often view our lives as a linear progression, a journey from birth to death. But if we inhabit a holographic universe, this notion becomes less concrete. Our existence could be akin to a series of overlapping realities, each one a different facet of the same cosmic hologram. This idea isn't just mind-bending, it's life-altering. But let's not forget that theories, as compelling as they may be, are not definitive truths. They are stepping stones in our quest for knowledge, tools to help us navigate the vast, complex cosmos. The holographic universe theory is just one of many interpretations of reality, each with its own strengths and limitations. As we delve deeper into the mysteries of the universe, we must remain open to new ideas, ready to challenge our preconceived notions and willing to embrace the unknown. For it is in this spirit of inquiry and exploration that we make our greatest strides, pushing the boundaries of our understanding and venturing ever closer to the truth. Whether or not we live in a holographic universe, pondering this theory expands our minds to the vast, fascinating possibilities of reality.